Hello and welcome to your Design Review event. We are pleased you could join us today and we've got some exciting things to share with you. As we continue to make our way through these difficult times and face the challenges COVID-19 is causing in our communities, it's inspiring to see how the student teams of Twente have adapted and remained fully focused. For us that meant working remotely from home and working on the boat only when necessary. As Starterboat Twente, we are supporting the energy transition towards a more sustainable world. By building a boat and competing in races, we want to inspire especially the maritime sector. We built our solar-powered boat in such a way that it uses the energy of the sun as efficiently as possible. Our team uses all kinds of innovative techniques to produce this boat, which Rick is going to tell you more about.
So every year we build a boat which will compete in several races. Our last and most exciting race is the big final in Monaco, the World Championships for the Solar and Energy Boat Challenge. To be prepared for these races, the team needs to design, produce, construct and test all the innovations within 1 year. This is a huge challenge. But luckily, we have a team of highly motivated students. In the past few months, the team has been working tirelessly on some improvements through the design phase. Today, each technical sub-team will tell you all about their plans and challenges to perform well in the races. So let's move on to our boat. This year we are able to use the boat that the previous team has produced. We will continue working on the boat of last year to reach our big end goal. As we do not start from scratch, we do have more time to optimize the current systems in the boat and have a longer testing period than previous years. We will grab this opportunity to actually fly above the water and reach a stable flight with our boat. Yes, we will fly. Flying reduces the resistance of the boat, which saves a lot of energy. In the rest of this presentation, the team will show you how we will fly, starting with a small introduction about our current boat.
Last year's team designed a very lightweight boat of 118 kilos. This year we strive to keep the boat just as lightweighted or try to make it even lighter where possible, since gravity is the main force to overcome. In order to fly, we need to generate a lifting force that is equal or greater than the force of gravity, which pulls us down due to the weight of the boat. But besides the amount of weight, the distribution of weight is also very important to control the boat. The upward lifting force and the downward force of gravity do not only need to be equal, but also at the same location to ensure a stable flight. Therefore, we designed our boat and distributed its components in such a way that the center of gravity is located at the center of the 3 upward lifting forces generated by the foils in the water. Team Hydrofoils will tell you now all about these foils and the system that controls our boat during the flight.
To enable our boat to fly, we'll be using a technique used a lot in the aviation industry to create an upwards force. We'll be using wings, or in maritime terms, foils. But instead of our wings flying through the air, our wings will glide through water. Due to water properties being different than those of air, Our wings can be much smaller than those in aeroplanes, being able to generate more force at lower speeds to lift our boat out of the water. We designed a mechanism which is able to control the angle of the foil with respect to water. Angle of attack is a very important parameter for the amount of lift, and together with the velocity of the boat determines the amount of lift generated. This mechanism needs to be fast and watertight, which are some of the challenges that we're facing this year.
To let our boat fly, we need to make sure that the foils are at a certain depth in the water. If they don't, the density of the water around the foil decreases, causing a huge reduction in lift generated by our foils. As a result, our boat dives or falls into the water, which is unwanted. The distance between the boat and the foils is fixed. A certain depth of the foils in the water gives a certain height of the boat above the water. In order to retain a certain height above the water, we use a so-called control system. Such a control system may sound vague, but it's in principle quite easy. Let me explain. A good example is the cruise control in your car. Imagine that you are driving in your car on the highway and you want to drive at a certain constant speed. Cruise control takes care of this. The computer compares your actual velocity and your desired velocity. If your actual velocity is slightly too low, because you have, for example, headwind, the car gives more power, so the car accelerates to your desired velocity. In this way, your desired velocity is met. Our control system does not regulate the velocity like in previous example, but it regulates the height of our boat. It compares a reference height and the actual height measured by sensors in our boat. Using our wings, we can adjust the height of our boat. The system makes sure that we can fly stable above the water. It also takes into account disturbances like wind and waves. It makes sure that we do not tip over with the tiniest amount of wind. There are a lot of variables that have to be controlled. While taking off and landing, the boat makes an angle with the water surface in the direction of motion of the boat. This is called pitch. Also, the boat can tilt perpendicular to this direction. This is called roll. During our stable flight, any pitch or roll is unwanted. It may cause our boat to fall into the water. Our control system makes sure that our wings compensate for any of these unwanted angles that the boat can make. In order to have a proper communication between our control system and our wings, there have to be a lot of communication and interactions between them. Manuel from Subteam Software will tell you more about this.
In order to have a stably flying boat, we need to be able to control it. This is where all the electronics that make up the control system come in. At the heart of the system is a lightweight onboard computer. This computer coordinates and communicates with all other electronic devices on board. It does so by communicating with them through CAN. This is a communication system that's used throughout the automotive industry and is simply two wires onto which all other electronic devices can be connected. This saves us having to individually wire each device to the main computer. The electronic devices can be categorized into two groups. Those responsible for the power management and propulsion in the boat, which my colleague Joris will tell you a bit more about, and those responsible for controlling the boat. In order to control the boat, we need to know its state. For this, we have sensors, namely a gyroscope and a height detection sensor, which collect information about the boat's current state. This is then sent to the main computer over CAN, and then the main computer calculates the necessary adjustments for the boat to correct itself. That's then sent via CAN again to the actuators which control the foils. So, for example, if our boat is tilting down to the right a bit, the sensors will collect this information. The main computer will then instruct the right actuator to move the foil up, thereby increasing the angle of attack and pushing the boat back to the correct position. This, of course, happens multiple times a second in order to keep the boat flying stably at all times. The principle of this system is relatively easy. However, to implement it, we need our own custom-made software. This year, we focus on making that software as modular and flexible as possible. This allows us to easily change settings or even swap out whole parts of the code with ease. This makes testing more efficient as we can change things more quickly. The focus of the software is also on collecting as much data as possible, as we want to know exactly what's going on inside our boat. Additionally, this year we want to implement a dashboard for the pilot to visualize all the critical data coming in from the boat. This will enable us to make better decisions while racing and use better strategies. The idea is that we can optimize for speed or for efficiency depending on our needs. So, as you're well aware, for a solar boat, efficiency is a key aspect, and how we use the solar energy as efficiently as possible is where the powertrain comes in. Joris can tell you a bit more about how we do this.
Thank you, Manuel. So the first stage in converting light to electricity is the solar panel array. We are using the same cells as last year, which have an efficiency of 24.8%. And because of their technology, we are allowed to use up to 6 square meters of them on our boat. In conjunction with the solar panels, we are using maximum power point trackers, which, as their name suggests, ensure that the solar panels operate at their maximum power point and harvest as much energy as possible. These have an efficiency of around 99%, but we will also integrate power sensors in them this year in order to have a better understanding of the energy flowing into the boat. When there is not enough light available, our boat is equipped with a battery which will provide us with the power we need. On top of this battery is a device called the battery management system, which manages the incoming and outgoing power, but it also protects the battery cells, and it uses a technique called balancing to make sure that as much energy as possible can be stored. This year, we want to improve the state of charge estimation algorithm. Knowing the state of charge, or in other words, the amount of energy that is available from the battery, is a vital parameter for making decisions and determining the race strategy. This year, we are facing another challenge, and that is controlling the temperature of the battery. The cells are very temperature sensitive, and they need to be kept within reasonable limits in order to not risk permanent damage. We are doing this with two methods. On one hand, we will integrate temperature sensors when making the battery. This will allow us to monitor the temperature and take action if necessary to prevent the battery from overheating. But on the other hand, we will integrate a liquid cooling system into the battery, which will allow the cells to stay cool at all times. Now, it is time to look at where all this energy is going. As you know from Manuel, the boat is equipped with a lot of electronics that control the operation of the boat. However, those electronics do not use that much energy. Most of the power is used to propel the boat. But how this is done will be told to you by the propulsion team.
The team of last year created a working propulsion system. The head of the system is the motor, which is enclosed by the nacelle. This combination will be below the water surface during sailing, which is called a pod motor. The big advantage of this configuration is the cooling, because the water flowing past the nacelle prevents the motor from overheating. This also allows the motor to convert electrical power into mechanical power at the right location, so there is no coupling needed between the motor and the propeller. A disadvantage of this configuration is that the drag is increased, since there's more material beneath the water surface. However, this is minimized by the hydrodynamic design of the nacelle. Also, our propeller is in front of our nacelle to make sure the water flow around it is undisturbed.
The driveline starts at the battery. The power of the battery is converted from a direct into an alternating current by the motor drive. The motor drive is also the communication system between the pilot and the motor. It translates the amount of throttle given by the pilot at the steering wheel into an amount of power that the motor can use to generate thrust. Unfortunately, this process is not 100% efficient and therefore generates heat. The propulsion system is limited by these higher temperatures, which tend to overheat the motor drive. To prevent from overheating, we are currently designing a closed-loop microfluid cooled system to dissipate enough of the generated heat. A proper cooled motor drive will allow us to use all available power.
The mechanical power from the motor is converted into thrust by the propeller. The design of the propeller determines the performance of this transmission, which has different requirements for the several race elements. Since we want to maximize acceleration for the sprint and slalom and efficiency for the endurance race, we will design two propellers. We will optimize the design of each propeller according to the other properties of our propulsion system. Also, we will keep it lightweight by using aluminum. That is how we will improve our propulsion system and perform to our full capacity during all race elements.
This event marks the end of our design phase. I am very proud of the work that has been done over the past few months and the people who made it all possible. At Solarboat Twente, our mission is to design and build a solar boat that empowers and inspires people to commit towards a more sustainable future, especially in the maritime sector. This is something we would not have been able to do without the help of our partners. We are very happy to have you on our team. We'd like to say a special thanks to our main partner, Lumen Business Solution, who also advises us on our planning to make sure we do not only grow on the technical aspects. I hope you are looking forward to our new improved boat as much as we are. If you have any questions or suggestions, you can stay a bit longer or send us an email. For now, I'd like to say thank you for joining, stay healthy and enjoy your evening.